So in this plug, we play around with the continuous random variable and the probability density function. So we have a random variable, which we call x, and you should have some kind of an idea what the random variable is. We have r, which is the range of the random variable, the possible values that x can take. And we also talk about discrete and continuous random variables, where the distinction between them is in the range of the random variable. To make a clear distinction between discrete and continuous is a little bit tricky mathematically, but it's typically enough if you think of a discrete random variable as one with a range which is like 1, 2, 3, 4, 5 and so on, and a continuous random variable one with a range which is an interval of the real line or the entire real line itself. But there are actually random variables which are neither discrete nor continuous. If x is a discrete random variable, then we define a function f of x as the probability that the random variable x takes a particular value small x, and we call that the probability distribution function. If x is continuous, on the other hand, then this probability is equal to 0 for every x. That may be hard to buy because a random variable must take one value, and it seems like if the probability is 0 for every x, then the probability should be 0 for any x. But that turns out not to be the case. So let me try to give you an argument for why this probability must be 0 if x is continuous. So let's say you have some radioactive material which emits alpha particles, for example. And let's say you define x to be the time to when the first alpha particle is emitted. So think of px equal to pi. Pi here being 3.1415 and so on. So that's the probability that the alpha particle is released after exactly 3.141592 blah 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 so and so seconds. So when we write the probability that x is equal to pi, we mean actually literally the probability that the release of the first particle is equal to pi to the last decimal. Every decimal from the first all the way to infinity should be exactly as pi. Now there is only one reasonable probability that you can give to such an event, and that probability must be 0. So keep that in mind when we write for a continuous random variable probability x equal to pi. We do not mean the probability that x is close to pi. We mean the probability that it's exactly pi. Well, that of course means that the definition we have for a probability distribution function is completely useless if x is a continuous random variable. Instead, every continuous random variable has something called a probability density function. Now, it is an unfortunate fact that defining what such a probability density function is rather tricky. This is the definition of a probability density function, which I picked up from Wikipedia, which is pretty close to how most people would define the probability density function. In some simple cases, you can actually define it as the derivative of a cumulative distribution function, but unless you have the necessary mathematical training, I would actually suggest that you skip the definition of the probability density function altogether. Instead, focus on how to use it. So just accept that both discrete and continuous random variables have an associated f of x. They have different names. For the discrete one, it's probability distribution function. For the continuous one, it's probability density function. The definition in the discrete case, simple. Definition in the continuous case, hard. So just accept it. Every continuous random variable is dragging along its own PDF. And in probability theory, this PDF is given to you. So let's instead focus on how to use it. So the main result is as follows. So on the left hand side you have a probability. That's the probability that the random variable will give you a number in between A and B. So here we focus on probabilities of intervals rather than probabilities of x taking a single value, since the latter is 0 if it continues. On the right hand side it says that you can always compute such probability simply by integrating the function, and the limits of the integral are precisely the limits of the interval for which we want to know the probability. So the graphical representation will look something like this. I have the real axis here. I have a continuous random variable. To this continuous random variable, I have an associated probability density function, and let's just say that the PDF looks something like this. Doesn't really make any difference at this point. So that's my PDF. Let's say that I am interested in finding the probability that my random variable will give me any number between A and B. Well, the answer to this question is the integral of f of x. So I draw vertical lines like this, mark this area here, and that is the probability that I will get a number between A and B. So let's look at a simple example. Let's say I have a random variable x. Let's say that the range is the interval between 0 and 1. Any real number between 0 and 1 is a possible outcome of x. And let's say that the random variable x has a PDF which is given by 2 times x. And I'm looking for the probability that x is less than a half. Well, since x can only take values between 0 and 1, that's exactly the same thing as the probability that x is greater than or equal to 0 and less than or equal to 1/2. So on the left hand side it says less than, but on the right hand side it says less than or equal to. Well, the thing is, it doesn't really matter if I include the 1/2 in my interval, since the probability that x will take precisely the value 1/2 is still 0. So for continuous random variables, it makes no difference if you use the less than sign or if you use the less than or equal to sign. By definition, this is the integral from 0 to 1/2. F of x is 2x. I write dx, and this is the probability. You can easily check that this is equal to 1/4, either by using Wolfram alpha, or in this case, it's very simple to see that the area is 1/4 because f of x is 2x. So if I have a 1 here, I have a 2 here, 1/2, I have a 1. So the area here is precisely 1/2 times 1 divided by 2, which is 1/4. So there's a 25% chance that I get a number less than a half, and there will be a 75% chance that I get the number which is greater than 1/2.